Hello friends, and welcome back to another Centennial video. We're doing number 12. So as usual, I want you to read this poem by yourself. Try to work it out. Try to understand what you can do before continuing on with the video. Alright? Try it out first. Okay, so assuming you tried it out, we got some methanol and water. Got 1,000 kilograms. They contain equal parts by mass, and they are to be distilled, okay? So this is a process in which we will be separating some parts of the methanol and the water. The product stream leaves the top and the bottom of the distillation column. The flow rate of the bottom stream is measured and found to be 673 kilograms per hour, and the overhead stream is analyzed and contains 96 weight percent methanol. Okay, so we're going to start by drawing what the schematic is. So here we have the feed stream, and we have this block representing the distillation column, which separates from the overhead and the bottom stream. Okay, so filling this in, we have 1,000 kilograms per hour, equal parts by mass. So that means we're going to have 0.5 kilograms of methanol per hour. We use MEOH for methanol, and that means also 0.5 kilograms of water, okay, per kilogram. Excuse me, not per hour. And continuing on this, well, let's see what it says here. The overhead stream, right? The overhead stream has 96% by weight of methanol, so that means it's 4% by weight of water. And finally, we have the bottom stream, which tells us that we have 673 kilograms. So we don't have the mass fraction, so I'm going to use W to represent the mass fraction of methanol, and subtracting 1 minus W would give us the mass fraction of water. Okay, so what we have to do is the degree of freedom analysis, and that's just going to be, well, we know that this is the feed, this is the distillate, and this is the bottoms. So we can write an overall mass balance, and we can also write a methanol mass balance. So we're going to have two equations. And then the two unknowns are going to be the distillate and the mass fraction of methanol. So what we do is we subtract the number of equations we can write by the number of unknowns, which is going to be 2 minus 2. So the degree of freedom is going to be 0, which means that we can actually solve this problem. Remember, if it's non-zero, then we can't solve this problem. Okay, so now we got to do is calculate the mass and mole fractions of methanol and the molar flow rates of methanol and water in the bottom product stream. Okay, so the first thing you can do is the overall mass balance. Remember, adding up everything that's going into the system and setting it equal to everything that's going out. So it's going to be 1,000, right? Right, the feed is equal to the distillate plus the bottoms, right? Right, the overall mass balance, plug it in, 1,000 equals 673 plus the distillate. And look, we can quite simply solve for the distillate, right? And if we plug these values in, we're going to have the complete overall mass balance, okay? And next, we can do the methanol mass balance by similarly adding up the methanol going into the system and all the methanol leaving the system. And what's going in is about 50-50 ratio of methanol to water, right? So we're going to multiply these values and set them equal to the multiplication of these values, multiplying these values. All right, so if you plug in those numbers, it's going to be 0.5 times 1,000, right? And set it equal to 0.96 times 327. This is the distillate. And 673 times this this mass fraction. And we can use some algebra to solve for this mass fraction, because we already solved for the distillate concentration, the distillate flow rate, excuse me. And doing some algebra, we can solve for this. It's going to be 27% methanol per kilogram in the bottom stream. So notice how it has begun to separate quite a bit, where here we have about 50% of the methanol, and here we have 96% of the methanol. But the bottom does contain less methanol, and this contains more water. So basically, what this is doing, this is a separation process that is separating the methanol and the water. See how it's becoming a little bit more purified? Great. And let's see, now we have to do some calculations, the molar flow rates. Remember, the definition of the mole fraction is, well, the molar flow rate of component with respect to the molar flow rate of the stream, okay? And knowing the molecular weight of water, molecular weight of methanol, remember methanol, if you take an OChem, it's going to be about 32 grams per mole. Okay, so what we need to do is convert the mass flow rates that we have into molar flow rates. To do that, well, we have the mass flow rate in this case of methanol, by multiplying. 96% of 327 is going to be about 313, and 27.7% of 673 is going to be about 187 kilograms. So what this is I'm getting the actual the mass flow rate of methanol in the stream, okay, not just the molar flow rate, and not just the overall flow rate, the mass flow rate. So now using these values and using the molecular weight, I can do some unit conversions, and I can obtain the molar flow rate of methanol in the bottom stream. Okay, so I didn't actually really need to calculate these. I actually already know the mass flow rate here, and I can use that to get the molar flow rate of methanol in the bottom stream. Okay. Similarly, I can do that for the water stream, which I can multiply again and do these calculations. And again, instead of using 32 grams per mole in this case, I'm going to use 18 grams per mole. And notice how I did these unit conversions of moles to kilomoles. If you need to review unit conversions, I highly recommend checking out Chapter 2 problems in the beginning of this playlist. Great, so now we have these molar flow rates, and now what else do we need? We need the molar flow rates of the methanol and water. And just as an overall check, we can see that the overall molar flow rate, mole balance is going to be adding these together, right? So now this is the total molar flow rate of the bottom stream, right? Because it's the molar flow rate of the methanol plus the molar flow rate of the water. So now this is the molar flow rate coming out of the bottom stream. And using the same equation that we have up here, now we can solve for the mole fraction, right? Which is going to be 0.176. Okay? Mole fractions of methanol. Great. So now we have everything we need to solve for the mass balance. And now suppose the bottom product stream is analyzed and the mole fraction of methanol is found to be significantly higher than calculated in part B. So it's going to be much greater than 17%. This has many possible reasons for the discrepancy, as you can think of. Include in your list possible violations of assumptions made in part B. So this is where the engineering really takes place. You got to really start to analyze the system and think more outside the box. Okay, so outside the stream, well, what could be possibly going on? You know, maybe there's some error, maybe there's some issues in the distillation column. So this is what I came up with. So the distillation column uses heating to separate the product from the bottom stream. So perhaps the heating is higher than expected, or lower than expected, and there's a loss of temperature control. Okay, one of the classes you have to take in chemical engineering is process control. So how do you optimize your processes so that you get the desired outcome that you want? Another example is a non-steady state or dynamic process. So, you know, in this case, we're assuming that it's steady state, just a general assumption, but maybe it's actually non-steady state. It's not fully optimized to be an equilibrated system. Perhaps there's some detection error. You know, it says that it's just analyzed. Okay, well, what does that mean? Is the detector not working properly, or perhaps there's a possible human error? You know, that's another example of analyzing this type of system outside the box. Or perhaps there's even impurities in the system, maybe even a reaction occurring. Maybe there's some other stuff other than just methanol and water. So maybe these are some possible assumptions that might have been wrong, or some other impurities in the system. Okay, thanks for watching. This is a relatively short video. Don't forget to check out the playlist and share this with your friends, family, and your dog.